right? Nisa, can you please, Nisa is here. Can you please let me know how many of you are still in industrial training? Then I will wait until everyone who's not in training is done. So I'm not going to do the lecture for 6 of you. Please let your batchmates, please ask them to join since I need at least 10 of you to begin and continue the lecture. Otherwise, it's quite easy. All right. So am I audible now, sir? So can you hear me now? All right. Okay. Uh, so what I said is I need at least 10 of you to be present in the lecture. At the moment we have 8. So once 2 more join, then I'll begin the lecture. So please ask your batchmates to join as soon as well. Get it? We can begin the lecture since you have 10 students. If any more guys want to join, please ask them to do so, but I'll begin the lecture and continue. So it's possible that I might not be audible. You may having some issues with my microphone and so on. So if at any point, if you can't hear me, please unmute yourself and let me know. And then I will rectify the issues and continue from where we see. Let things on. Okay, so welcome to ETM4233. The module name is Robotic Technology and it's our first lecture today. And once again, so those who are in the mechatronics system modeling lecture got the opportunity to got the opportunity to listen to me going through this slide. But once again, I want to iterate the fact that if you have any issues, please raise them in the WhatsApp group. Sorry for that. So where was I at? Yeah, we were discussing learning outcomes, which are specified the in your module descriptors. Right. So just a small checkup. Can you hear me and can you see my screen once again? I'm doing a small check since I disconnected and I'm connected again. So Misara, can you please let me know if you can see the screen and can hear me?
Yes, sir, we can hear.
All right. Okay. So learning outcomes. So you have kind of three learning outcomes which are related to describing stuff. You should be able to describe the types of robotics and the classifications of robotics. So this is what we'll be doing today. We have the focus of lecture one would be on giving you giving you the knowledge required to obtain this learning outcome. And the next is there's something called kinematics and dynamatics for both robot manipulators and mobile robots. So at the ends of let's say lectures 2 to 6 or so, the knowledge you gain from that will make you able to describe this stuff. And afterwards, in building up on kinematics and dynamatics, sorry, kinematics and kinetics or dynamics, then we should be able to develop code which would run on microcontrollers and so on, which would enable robots follow the required motion uh, by the required path specified by whatever path profiles that you present. And so the first one is kind of not related to theory, but very low level stuff. And learning outcomes 2 and 3 are related to kind of the mathematics behind the robotics. Number 4, which is to analyze and design robot cells, collaborative robots, and so on and so forth. It has a more practical approach to it, and it will be. So my plan is to teach you a robot programming software called Robot EK, and gaining proficiency in that software would enable you to obtain this fourth learning outcome. So moving on, this is an excerpt from the module descriptor for ETM4233. So according to it, we should spend 6 lecture hours on getting an overview of robotics, but I'm not going to spend any more than 2 hours. So in today's lecture, I will give you an overview of robotics, and that will be all. And from there onwards, I'll be moving on to kinematics and kinetics, and finally something called differential motion. This is where we discuss how to write code to obtain required robot motion. And yes, and finally, not finally, but in parallel, we'll also be discussing the practical aspects of robotics, or to be more precise, practical aspects of industrial robot manipulators. And as I said earlier on, this will be done through the use of programming software called Robotics. So now that was the module descriptor provided to us, and this is the roadmap that I have prepared. So basically, the same thing that I discussed earlier on. So today we'll be discussing type of robotics. Then perhaps lectures 2 to 4 would be on modeling the robots, objects, and space. So in this particular area, we will be discussing how to describe problems to programs. And from lecture 5 onwards, we'll be discussing how programs tackle what the programs tackle solving the problems that we described to them. Yes. So we'll discuss what robots are. We'll discuss how to describe problems, and we'll discuss how problems are solved using programs and so on. Now, this is the theoretical aspects of robotics, and the accompanying software package would be the robotic systems toolbox in MATLAB. Right. So I expect you to have a fundamental grasp of MATLAB. And as I mentioned in my first lecture on ETM4233, if you don't have that fundamental graph, then you can check out the MATLAB on-ramp free courses provided by MATLAB and quickly gain that knowledge. So robotic systems toolbox is an add-on provided by MATLAB in the ecosystem, and I'll teach you how to use that. But you need to have the fundamental grasp on the core stuff for MATLAB stuff, right? So we'll learn the theory and we'll use the systems toolbox to put the software to work. So that's software number one that we'll be learning. And then we have the practical aspects of robotics. There we'll learn programming robotics using something called the teach pendant. And then we'll program the robot using CAD references. Simply put, we'll be obtaining motion paths just from CAD. We won't be specifying the robot path ourselves, but we leave it up to the software to determine what's the best and most optimal paths that is required based on the generic type of task. So these are two methods of programming robots. We'll do them both in a virtual environment provided by Robotics. And finally, we'll put to use what we have learned on programming robots. In addition to programming robots, we should also be able to design the upstream conveyors and downstream conveyors, any jigs and fixtures that should accompany robots. So all that is encompassed in robotic cell design. And yeah, that can also be done using this software, and I'll be teaching you that. Maybe that those will be the practical aspects of this one. Right? Okay. So we'll be doing these things parallel. Say, I make decide in between. As for the references for this whole module, the book Modern Robotics, written by Kevin Lynch and Stephen Park, I guess, is what's recommended by the module descriptor, and also this is what I've used when I was learning robots as well. But however, I've also found this other textbook called Introduction to Robotics, Mechanics and Control, written by a person called Craig, to be very descriptive on the mathematics required to describe problems and solve problems. So it is more simple than the modern robotics book, and I'll be using content from the first book in my lecture, so it will be easier for me to describe and easier for you to understand. So if you are going to read a book, I will suggest that you first read the first book that's mentioned earlier by Craig. And once you master what I taught you, then you can go to modern robotics and for you later activities. Okay. And as for the software, of course, you should have MATLAB installed. And when installing MATLAB, you should have the robotic systems toolbox add-on installed as well. So I don't think this is available in MATLAB versions below 2020. I have 2020 and 2021. I had both installed, so you should have a MATLAB installation later than 2020 in order to use robotic systems toolbox. So even if the earlier versions had the toolbox, it wouldn't have all the required functions that you would need to perform this, right? So please make sure that your MATLAB installation is later than 2020. So if you don't know how to go to get into PC and download the right version, install them in PC. Now, to do the practicals of this module, you should have Robotics installed. So you can simply Google what Robotics is. We'll direct you to the official site and you can download the trial version. Now the trial version is what I am using as well. So uh, it's sufficient for what I am planning to do, and also it's so unless you are doing industrial work, it's all right for us to have the trial version. That would be enough for us. Cracked versions of the full version, the cracked full versions are also available, but I don't recommend using those since there are some issues with the licensing and they will crash in the midst of running stuff. So just download and install the trial version of Robotics provided by the official website. That would be it. Now, in addition to what I am teaching and what's being presented in these texts, there are a few online learning resources that you can refer to as well. So I wasn't able to add the links to them, but for the general theory, there's I think a website called Queensland University of Technology Robotics Academy, maintained by a renowned professor in robotics called Peter Koch. I provide the link to that later on. So if you have trouble keeping up with what I teach, you can refer to those set of videos on QUT Robotics Academy. And when it comes to learning the robotics software, you should refer to the robotics tutorials available on YouTube. So that's the official and only means of learning this software. And later on, we will also use the online documentation for the robotic systems toolbox and robotic as well. But I'll let you know when to refer to those. And as for the method of assessments, it's same as my other module. We have a 70 and 30 distribution of marks for the end semester and assignments, entrance assignments. Once again, you are allowed to bring a sheet of paper with your notes for the end exam. All assignments will be individual and you have 3 assignments. So one would focus on using the MATLAB toolbox for robotics in order to solve kinematic and dynamic problems. One is specified it. And the second and third would be about putting to use the robotic programming techniques that we use and to develop robot cells. So once you finish the second and third assignments, you will have some virtual robot cell with you, which you can, yeah, it's kind of, you can also end up with an animation or kind of digital twin for a robot cell, which you can showcase, go for videos and stuff. Right? So not always full assignment. Right. So that's it for the generic information about the module. So we can begin lecture 1. So as I told you earlier on, I'm going to provide a general overview about what robotics is and how we can break certain robots down into classes and what certain types of robots are. So the learning outcomes of today's lecture would be you should be able to give a brief description on the history of robots. Should be able to classify robots and kind of explain to someone who doesn't know what the applications of robots in industrial automation. Okay, so we come to my entry point for any module, which is the definition of something. Yes, okay. So I'll speak a bit louder and a bit slower. And if you still have trouble hearing me, then please let me know and I'll rectify those issues. So coming back to our entry point, the definition of a robot. So now the Merriam-Webster dictionary provides 3 definitions as it did or what a mechatronic system is. Now, the first definition is that it's something or a machine that resembles a living creature in being capable of moving independently and performing complex actions. By the fact that by the word resembles, it means that it should look like and also behave like a living creature. But from the phrase a living creature, we can say that it doesn't necessarily mean a human, but any kind of living animal. So a machine looks like a living creature and behaves like a living creature, then you can call that a robot. And then there's another definition, a device that automatically performs complicated and repetitive tasks. So if a machine performs something over and over again without supervision from a human, then we call that a robot. And the second definition is what fits most industrial robots that we see in manufacturing, right? So they do repetitive tasks definitely and moderately complicated and without any human supervision. Initially, they have some supervision because someone has to go and program them, but afterwards, they can perform these tasks without any supervision, so we can call them automatic performing. So this definition matches what we see in most factories and so on, I would say in manufacturing. And the third definition, so it discusses mechanisms guided by automatic control. So it's a very vague definition. Uh, so I'm using this definition. Any machine that operates autonomously would be called a robot or classified as a robot. Since it's very vague and broad, I don't think this is going to be useful. Right. So that's the definition, not really useful to us, but that's my entry point. And we learn a few key phrases from these definitions and move on and observe case studies and observe robots and see how they fit into these definitions. Right. So one question before we proceed. So how about the audio and is it still low and is it still breaking down and so on? Because if it is, I can once again speak louder and slower. I don't know what the issue is. So Misara, if you are there, can you please let me know if the audio is okay or if the current status is okay or not? So I'll continue at this. So we finished our definition and now we are okay. So let's dive into the history of robotics. So I'm not going to spend much time over here. Now the word, as you can see from the definition we saw in the previous slide, robotics is a very broad term and it involves a large amount of variations and so on. I can cover all these variations in a single lecture and in a single module. We don't have time to do that. So I am restricting myself to robots that we see in industrial cases, in the manufacturing industry mostly, while still touching on a few military and such robots as well. So for me, all the interesting stuff in the domain of robotics have been after the third industrial revolution. Right? Now, the first industrial revolution is where they mechanized the human. Right? So they built custom machines which can, yeah, which can automate what a human does, perhaps even faster as well. But emphasis on the word custom. So those machines can't be reprogrammed or rebuilt to do any other task. Once they are built for a particular task, then that's it. That's all that they can perform. They don't have any intelligence in them. They were purely mechanical. So in the first industrial revolution, they didn't have any of these computers. But all they had was mechanisms and all machines that they built were completely mechanical. And the second industrial revolution where they introduced the assembly line, the associated fast mass manufacturing. Even then, so this was in the 1910s and the 1910s and 20s, the second industrial revolution. And even then, they didn't have robots which were kind of generic. Now, generic industrial robots were developed with the advent of the third industrial revolution. So in the 1950s or so, perhaps the late 1940s or the early 1950s, they developed computers, not the digital computers that we see today, but at least some devices which were programmable and had memory. Right? So I would say machines which were assembled during machines were developed in the late 1940s. They had memory and they were reprogrammable. And having such devices enabled people to build robots which were programmable and reprogrammable. And these robots weren't limited to a single custom application. Since they were programmable, they were people were able to use a single robot for different kinds of applications, and that gave the rise to generic robots. Now, what you see over here is the world's first programmable robot, which I think has 5 or 6 degrees. I can't exactly remember. The name of this model is Unity, and it was developed by a single person called George Evol, and subsequently he formed the company called Unimation, which built was like. So I think it's a 5 degree of freedom robot. So the next robot built by Unimation was the Unimate Puma. That was a 6 degree of freedom robot, general programmable 6 degree of freedom. So this is the first programmable robot in the world, and from here onwards, people began to build general purpose robots which were reprogrammable, and then the industrial revolution grew up. Robotics, industrial robots at least, was soon accepted, so soon ubiquitous in factories all around. Now I do have a video of the unit built by Unimation. Let's watch it and come back. Right. So there are a few things that I want to focus on. So the first programmable robot, and yes, it was a hydraulic manipulator arm. So I think this was developed in the 1950s. can't remember exactly, but back then, the motors with a high power to weight ratio and high power to volume ratio that we have today weren't available back then. So what they had, what the actuators that they had, which were capable of actuating a robot arm like this, were hydraulic manipulators, and so therefore they use hydraulic manipulators. But today, apart from a certain types of robot which still use hydraulics due to having to lift items such as cars, or the other robots are now running using electric motors, AC or DC. And they say that it was used by car makers to automate metalworking and welding processes, but I yes, so there's another more descriptive documentary on this robot. If you have time, check that out. So what they use it for, uh, the one application was to remove die castings out of a die cast press, and it was a very hot environment. So that was one of the first things the automated did, removing die castings and placing uh, the die were prior to casting, and some metal welding processes which gave off toxic fumes. And in order to prevent the workers, they use robots to do it. Right? So that so at that time in the 1950s, the biggest companies or the companies which had the financial capability to invest in robotics were car makers, particularly the car makers in Detroit, USA, the GM, Ford, so on and so forth. So they were the guys who had the financial capability to purchase $200,000 robot lens. Right? So in today's world, so today's money, this would roughly be worth 200,000 US dollars. But however, the world of robotics has come far from what the limit offered, and now we can purchase robots which have more capability than this for around $2,000. For $200,000 today, you can even purchase the human android, and also that is electron. And more importantly, yes, there are two more stuff that I wanted to emphasize. Its memory had hundreds of program space. Now, in that documentary I was talking about, they described that in order to program this robot, you had just had to lead it through the motions once manually. So in robotics jargon, that's called jogging. You had to jog it and push it once, and that was limited to 200 program steps. And yeah, but today I don't think there's any such limitations. In perhaps you can go into billions and billions of program steps. We don't need. And more importantly, this robot has a precision repeatability within 1 millimeter. And today that has really gone down to 1 micrometer. So 1,000 times improvement has been seen within 70 years or so. So we'll discuss what repeatability is and also what that is later on. But just keep in mind, world's first programmable robot is had a repeatability of 1 millimeter. Right, so that's it. That's all that I want to show you from that video. So prior to the third industrial revolution and the unit, the world had was something called automatons. So basically, custom built mechanical machines, but they were able to mimic the behavior of humans. So they were able to mimic the behavior and the appearance of humans. Therefore, by definition, these could also be considered as some kind of robotics, but I don't really find them interesting because other than entertainment, there are really no other industrial applications for these. But I have given you a few YouTube links which you can check out. You are interested in this stuff. But fun fact, even though these aren't interesting, these kinds of humanoid automatons can be traced back to the ancient Greek civilizations and even more as well. While some say that even in some Jataka tales, these kind of automatons were also mentioned, but I didn't found any such references. Okay, in my opinion, robotics really, not in my opinion, but as a fact, robotics really blew up after the third industrial revolution. And what we have today ubiquitously, at least in the manufacturing industry, are kind of grandchildren of the unit. Right. So the Unimate kind of gave way to a class of robots called industrial manipulators. But today we have more classes of robots. We have self-driving vehicles, uh, but they don't really resemble human appearance, even though they resemble human behavior. So I'm not going to touch them in my lecture. If you're interested, you can check them on yourself. Uh, the other class of robots that's relevant, since they mimic both the appearance and the behavior, is humanoid robotics. Now, the world really delved into humanoids with the Honda Asimo. So this was uh, released back in 2004, right? And then we have, so developed by Honda, of course, you may have seen videos of this. It's a very popular robot. And then you may not have heard of the super droid Rocky. So super droid is actually a company run by around 5 or 6 engineers. So it's a very small company, but they do have a humanoid platform of their own. So a few years back, they only had this platform which achieved mobile traversal using a wheel platform, but their humanoid torso was able to mimic human behavior, or at least mimic human torso behavior, and achieve construction tasks like what it's doing here. So it's holding some kind of drill in the same manner that a human construction contractor would hold. So I made a reference to this company and to this product just because it's remarkable as to what a small company like that has achieved. So compared to these other companies, so it's a very small company, I think in Kentucky or somewhere, by people, and really amazing at what they have done. And fun fact, they now have a biped version of their Rocky, I think Rocky Gen 2, and it can kind of walk like these other humanoids, but not that well, but still remarkable as to what they have done. And then, of course, you may have heard of Atlas. So I have the Atlas version 1 and Atlas version 2. Now, the version 1, you may have or may have not heard of this, but it was complete. It made use of hydraulic actuators for all its joints. There weren't any electric actuators in version 1. And version 2 onwards, which was released, I think, 2 or 3 months back, now it all depends on electric motors. Right? Now, their forte is agile humanoid performance. Right? So that was what they are focusing on. They have a very high they have a team which is very capable in the domain of model predictive control and so on. Control systems and agility is what they focus on most. They really haven't ventured into industrial applications yet, but they are perfecting now. I don't believe they have commercial versions of the humanoid yet. They have some dog robot called Spot that might be available commercially, but the humanoids aren't available commercially yet. So now from China, Chinese company called Unitree, we have the H1, which is available commercially, and last I checked, it was in stock. It, uh, it has a retail price tag of 150,000 US dollars. So I guess that must mean 50 million or so. I don't know what's the tax, Sri Lankan tax per humanoid robots, but so if you were to purchase and this, you would need, and if you had 50 million, you would be able to. It has a height of 180 centimeters and a weight of 47 kilograms. So it's important because these statistics quite resemble what an average human would have. So I think 180 centimeters comes down to 5 feet and 8 inches or so. So kind of average statistics for average person. And it has a walking speed of 1.5 meters per second. And if you can take a look at the videos, it can its resistance to minor disturbances as well. And then I want you, before we move on to the Sanctuary Phoenix, I want you to take a look at the arms of the Atlas, the unitary. Now they really don't have the dexterous fingers in them. So at the moment, these two companies focus on mobile agility, but not really what it can do with the arms. So now that's where Sanctuary Phoenix, which is a Canadian company, comes to play. Now their philosophy is to exactly mimic the human physiology. By that I mean all the dimensions here are exactly similar to the average human. It has a 5-fingered hand, which also has the equal degree of freedom to a human hand. And they also have some. They are also developing some AI program. I think perhaps called Carbon AI, which they say that exactly resembles the human mind. At the moment, this can't operate autonomously. So all the demonstrations done using the Sanctuary Phoenix have been done using teleoperation. But the good thing about teleoperation and learning techniques is that once people do enough teleoperated operations, the learning algorithms will be able to develop its own set of rules as to what it should do when the environment changes. Right? So when it has enough training data, it will be able to operate autonomously. So with the Carbon AI and the exact human physiology, soon it will be able to mimic all human behavior. Now all these three robot models and robot companies have been working on humanoids after the advent of deep learning, which was in 2012, I guess, after the ImageNet achievements. Now, the Honda Asimo was built in 2004 prior to all the deep learning hype, and it's completely based on all the control algorithms are based are kind of rule-based algorithms. So I think an extreme amount of effort has been done to develop the Honda Asimo compared to the other three, even though it doesn't have these kinds of robots performance. And the Rocky, on the other hand, I really don't think they have that kind of features built in at the moment. Once again, this is also teleoperated. So I hope we pick up on a few keywords such as teleoperating and what kind of learning technique that they use. It will be useful when it comes to robot classification, which we'll discuss later. And then we have something called the Robot Hall of Fame. It is maintained by the Carnegie Mellon University in California, USA. No, I don't know. It's California, but whatever. This Carnegie Mellon University in USA, so they maintain the Robot Hall of Fame. It doesn't really have anything to do with the technological advances, but rather the popularity of robots is what they really track. So they have two NASA rovers in the list. Other than that, of course, they have the Unimate. This was the first programmable robot. Aside from that, they have the Honda Asimo, Sony Aibo, Navo, which are robot models that the general public is familiar with. This is the now the Aibo and the other, yeah, Asimo. I didn't show it. I had a picture back. So now these robots really can't do anything, but there are people are it's popular among the general public. So they have included in the Hall of Fame. So this Hall of Fame is more of a popularity contest than anything else. But there are a few entries, like the Unimate, which I consider to be important and should be included in something like this. And if you track these important entries, then you'll be able to obtain some information as to how robotics has progressed throughout the ages. So we have the Unimate, first programmable robot, and then we have the Shaky, Stanford Shaky, which is the sorry, the Stanford Shaky, which is the first mobile robot developed by, of course, Stanford Uni, and the world's first SCARA robot developed by a Japanese university. And then we have the Raybird Hopper. So the Raybird Hopper, this doesn't really do anything useful, but it's the first robot which was capable of jumping up and down while balance without falling. So it was able to maintain balance while jumping up and down. And at that time, it was a technological, extremely high technological achievement, and therefore it's in the Hall of Fame. Now, the Raybird Hopper was developed by an engineer called, I think, Mark Raybird, and he was the guy behind Boston Dynamics, and this was kind of the first robot, or I would say this was kind of the grandfather of all robots developed by Boston Dynamics. So as you can see, they really do focus on agility and agile motion. Yes, and the 2010s, the Roomba came out, and that was really kind of the first robot which did something useful other than entertainment applications, and which did something useful and was available to the general public at an extremely low cost, which I think was around $2,000 at that time. So now this product has been phased down. Xiaomi has taken over the market and offers these alternatives which are also better performing at a very low price point. However, back then when it was introduced, the Roomba quickly became quite ubiquitous, and I would say was the first useful robot for the general public. And for the doctors, they introduced the Da Vinci surgical robot, and even 15 years later, 2025, no one has really replaced the Da Vinci. Perhaps the Da Vinci company has introduced few minor modifications, but no certain there isn't any other surgical robot which can even come close to the Da Vinci. So a medical robot available to doctors. Yes, then the first one, kind of the leading surgical robot to this date. And this was also teleoperated. It is not autonomous, at least as of yet. Uh, there's another control station slightly far away, and the robot has, sorry, the doctor has to kind of plug himself into the microscopes of the control center and operate the Da Vinci remote. And in 2012, what developed by, I think, the same company that developed the Roomba. I'm not exactly sure, perhaps company name changed a few times, but however, this was kind of the not the first military robot, but the first robot which was used by many law enforcement agencies all over the world. The first military robot was actually something called the Goliath, developed back in 19 30s, right? But however, we'll get back to that later on. But so this is the first popular robot used in that particular domain, right? Then, according to our module descriptor, we should study laws of robotics. And there's something called Asimov's laws or Asimov's rules for robotics. There are 3 laws. I'm not going to discuss this in detail because I don't really find this useful. So it comes from a work of fiction. It comes from some book written by Asimov. I really haven't read it, but I have given a link to the trailer of a movie called I, Robot. You can watch the trailer or you find that entertaining. You can watch the movie and it will focus on these laws quite often. So it doesn't have any use in the domain of industrial robotics or service or military robotics. Just something that this guy has popularized through his works of fiction and now it has stuck. So I'm not going to waste my time on it. I'm going to spoke. Right. Then, yeah, we finally, I think, due to our kind of at least one-sided discussion that we had so far. So I hope that we have picked up keywords and listened attentively and gleaned enough information required to classify robots into multiple classes based on different classification criteria. So based on the person or based on the guy who is classifying. All right. Okay. Sorry. So Misa has a good question. He asked what teleoperation is. So now teleoperation is kind of the fancy word for remote control. Okay. Now when I say fully autonomous robot, means that without any human supervision, it can operate. So people say that robot has a mind of its own, or the robot follows a set of rules and makes decisions by itself without human intervention. That's autonomous robot, right? Now teleoperation is quite different. Teleoperation is, as I said, the fancy word for remote control. And by remote control, a robot can be controlled either by wire connection or by a wireless connection. Right? So this bot was operated wirelessly. The Da Vinci had a wired connection to that control station. And in that control station, there was some controllers quite similar to the game controllers that you see for a PlayStation or an Xbox were made available to the doctor. And the doctor use those controls in order to guide the motion of the robot. Okay. So that's what teleoperation is. Mm, and I think Sojourner was also semi-teleoperated. By that I mean, no, I don't. I'm not sure, but perhaps it had autonomous roving capabilities, and at some point, the control station in NASA took over to manually operate it wirelessly. In, I would say it's semi-delivery. Okay, so I hope you are clear about the meaning of the term teleoperation. You want think of remote control either through a wired connection or a wireless connection. So are you okay with that explanation? Right. Okay. This is stuff. Okay. Right. Now, where was I? I was discussing the fact that how a robot is classified is dependent on the person who is doing the classification. And so this is my opinion on how to classify robots, influenced by the different types of books that I've read. But if you read multiple books, you will see that people classify robots as they see fit. So it's not really a systematic thing. You can come up with another kind of classification. You can do that on your own. It doesn't really have any meaning. So classification is really done in order to compact the knowledge. But let's take a look at how I classify things. Now, I classify robots according to operation, mainly industrial robots. They can I can break them into two classes based on operation. One class will handle object manipulation, and the other class will handle mobile traversal. For an example, there are 6 degree of freedom, articulated, Cartesian, SCARA, Delta, and all those robot arms I would consider as robots which do object manipulation, and AGVs, AMRs, and all that which you see in industry, I would call robots which do mobile travels. Right? So that's classification is based on how these robots operate. And secondly, these can be classified based on who the user is: industrial, military, commercial, education, domestic, and so on. Under industrial classification comes all the name branded industrial robot arms such as Kuka, Fanuc, ABP, and so on, which can be found only in manufacturing sectors. And when it comes to the military, I would say encompasses all the unmanned ground, air, and sea vehicles, which of course do things related or required by the military. And commercial robots would be things like the now that we saw, the Sony Aibo, and so on. And some service robots which are used for cleaning, waiting tables, and so on. And also the Da Vinci can be classified as a commercial robot in its medical robot use. And then we have education and research related robotics. So these robots which are lesser payload, higher repeatability. By higher repeatability, I mean higher magnitude of repeatability. Yes, and lower payload, lower speed, and very fragile robots that use fragile and cheap robots that you see, which are used for to teach robotics concepts to students and so on, not to really do an industrial work. And then we have domestic robots such as the Aibo and so on. Now there are few out there today, and some of them also, most of them provide entertainment, but I have found quite a funny application which is to provide, I think, mental support or something like that. I'm not exactly sure, but it has something to do with mental health. Okay. So those are domestic robots, and of course the Roomba and the Xiaomi vacuum robots fall into this category of domestic. Right. Based on the nature of mobility, we can classify them as either tethered or free. By tethered, I mean they are connected via wire to a control station or a power station, and which limits their range. And free robots would be mobile robots which can navigate freely without any tether and are only limited have a limited range only due to the capacity of their battery or over carrying capability. And also based on the nature of mobility, you can classify them whether they are land, air, or sea, or space road, based on where they are. Yes. Now comes an important classification of robot, that is classification based on the level of autonomy. Now at the lowest level of autonomy, we have zero autonomy. That means it's fully remote controlled or operated, which means a human has to be present. Without the human, it won't operate. even though it mimics the behavior and appearance. Without the human, it won't operate. So very zero autonomy. That's the operation. And then we have robots which can do tasks repeatedly once you. So you have to teach them manually the first time. But after that, they will be able to keep on doing that task, but in a structured environment. We will discuss what that is later on. And then we have robots, which once you teach them, can keep on working on the same task in unstructured environments. Now, structured and unstructured environments are okay. So, structured environments are what you see in industrial. So, what yeah, particularly in industrial assembly automation environments. Now they have input conveyors, output conveyors, jigs, pictures, and so on, arranged in a well defined and kind of static environment. So the environment doesn't really change. Even though there is movement, the environment is completely predictable. That means if you pick up a tool from one place, do the operation, and the tool must be placed back in the correct place. Kind of like a 5S environment. It is very clean, very neat, and very predictable. Those are kind of those are structured environments and mostly seen in industrial assembly automation and yeah, industrial environments, which require those clean, neat, and predictable environments. Now, unstructured environments would be what you see on a very unorganized person's desk. So, I don't know what you guys, but if I don't pay any attention to keeping my table or desk organized, in a few weeks or so, my items on the desk will be lying here and there. They won't be in the correct place. It would not be a 5S environment. It's not a neat environment. I wouldn't know where the tools are. And if I want to find out where my phone is, I had to use my eyes and scan around the table in order to figure out where the phone is, right? So that's a cluttered environment. I have no information, so I don't have knowledge about the current state of the environment, but using sensors, my eyes, I can figure out, I kind of figure out the current state after running the sensors, operating the sensors. So cluttered, unorganized environments or dynamic environments can be classified as unstructured. Now, the simplest example which I can use to make the difference, to kind of exaggerate the difference between those two environments is in a structured environment, your robot would not need any kind of sensors. Let's say you have a screwdriving environment, screwdriving application. If the robot requires multiple screwdrivers and has multiple items into which the screws must be driven, if the robot keeps track of where tool is kept, and if he also always keeps a particular tool in its uh, dedicated location, then without any sensors, whenever a new product comes in, he knows where to look for the screwdriver, the particular screwdriver, since he keeps things organized, since the environment is kept open. But let's say in an unstructured environment, the robot would use a screwdriver and just throw it away, and then another product comes in, the robot would have to use machine vision, scan the environment, and figure out where the screwdriver now is, and then move over there to the screwdriver and obtain it and come back and pick it up and come back and try this, right? So I hope that difference is quite clear. Now, if you were present in my MSM lecture, the example that I showed you has elements of both. Now the hopper, which has random components with random orientations in it, is an unstructured environment. But the conveyors coming in and coming out, they are structured, right? So if you find the meaning of these two words quite ungraspable, then watch that video and figure it out. Now, both these classes of robots, in whether to work in structured or unstructured environment, we should build, we kind of teach them a set of rules in order for them to function. And the last level of autonomy, which is the fully autonomous operation, is where the robot itself can decide what tool to pick, where to pick it up. If it's not there, look for it, make the decision to look for it and pick it up and so on. Right? So it behaves exactly like a human without the human intervention. Think of it as a human, but just a think of it as a tin can version of it without any emotion. So that's the highest level of autonomy that a robot can have. Okay, so that's it for that type of classification. Now we'll move on to one last. Now this classification is based on something called the kinematic configurations, which I'll get to in another lecture, in a later lecture. So this can be broken down into serial and parallel. Manipulators can be broken down into these two classes. Right now, it would be easier for me to simply show you two serial and parallel robots side by side. So what's on the right is a serial robot, and what's on the left is a parallel robot. So they essentially can do the same thing. There's no limitations as to what they can do, but how that motion is achieved is where the difference is. So I hope to see only what's for the video one. That's it in regards to serial and parallel manipulators are. Now, serial robots are what are mostly ubiquitous in the industry. Other than the Delta robot, the parallel robots are not really used that much. So when it comes to studying theory of robot manipulators, we'll be focusing on serial robots. We'll be studying dynamics and programming robots, implementing robot motion in microcontrollers, and we'll be focusing on serial robots. There's a reason why we do that. We'll discuss that when we get to those. Right. So I have a next set of examples from few industries. If you recall the definition of robot, they should mimic the behavior, or they should resemble the appearance, and they should resemble the behavior of some living creature in order for them to be classified as robots. Now on the top, I have some military robots, and at the bottom, I have some robots in the service industry. Uh, so one Russian robot, one German robot, one Estonian robot, and this is a military application built on a commercial platform. So there's a company called ClearPath, a US company, and ClearPath has a robot platform called the Husky. Now this Husky is used in commercial, military, and also education applications. And universities which can afford the Husky do so, and it's kind of a popular platform. And this is a demining application built on top of the ClearPath Husky. So I won't go into any more detail on that. Now, what you see underneath is quite more interesting than what you see above. We have a delivery robot developed by the Russian Google, I think. So Yandex is the Russian equivalent of Google. Yandex has a kind of similar robots to all the robots that Google is building. Now, this one resembles this one is a package delivery robot. Closely resembles some other package delivery robot built in the US, but I can't exactly remember what that brand was. So it's yes, it basically is a mobile robot with autonomous navigation. And apart from that, it really doesn't do anything else. Once you specify where to go to and where to come back, it navigates, it does the navigation, avoids obstacles, and follows road rules, I guess, at least pedestrian crossing rules. And it will deliver the package and come back. So essentially a simple mobile robot, nothing else. And then we have a robot brand called Dili, which was deployed by Pizza Hut in Singapore, I think. It also is essentially a mobile robot with autonomous navigation. And the cook, or I think whoever's employed in the kitchen, places these pizzas on top, and the guy or the customers pick them up. But apart from that, it's at the core of it, it's simply a robot with a chassis and autonomous navigation ability capability. But these three, which we see over here, are quite more complex than that. I will focus on the Lions bot first. Now, this is a company from Singapore. Actually, company founded by a university professor in, I think, Singapore University of Technology and Design. Can't exactly remember. But however, the whole company, Lancebot, is dedicated to building floor cleaning robots. They have a lineup of around 10 robots, and all they do is clean the floors, and based on the type of floors and the type of dirt and the rate at which the floor needs to be cleaned, they have different models of robots. Once again, these things are also mobile robots. So, if we take a table weighting robot and design a cleaning tool and attach that cleaning tool to that table weighting robot, we'll get a floor cleaning robot. So moderately complex, but not that groundbreaking. Of course, we have some solar panel cleaning robot. I think this has two components, one which moves on top of the solar panels and one which moves on the ground. And now, most importantly, I find this important or exciting because last year we kind of initiated a project to build one of these on our own at the university. So now, I can break this down into three components. First, we have the mobile platform, and then we have the telescopic reach platform, which can now this platform can be raised up to around 4 meters in a telescopic manner. So that's number two. And the third component is the painting tool. Now, we've already developed the painting tool at least to some considerable extent last year at the university, and this year I was hoping to build a mobile platform and the reach platform, and then put them all together and come up with a locally developed version of the preparation wall preparation robot. By wall preparation, it means plastering, some wall grinding activity, I guess, what they do with the sandpaper and painting. Quite simple and not that complicated. Once again, yeah, compared to what we see at the top, these things are quite less complicated and can be built by undergrads as well. So from here onwards, from this slide onwards, towards the remainder of the lecture and towards the remainder of the module, my focus will be exclusively on industrial robots used for industrial automation, right? So now industrial automation can be broken down into manipulators and mobile robotics, as I mentioned earlier on. When it comes to manipulators, I have observed that there are mainly manipulation can be broken down into three categories. First is object manipulation or pick and place of object. Now, by objects, I would mean items like this: finished items from a CNC machine, finished items from an injection mold, semi-finished items in an assembly automation operation, so on and so forth. So those are what I would call objects, and moving those objects around using a robot is a pick and place of objects. Then you have tool manipulation. By tools, I mean welding sticks, screwdrivers, spray cans. Even though I haven't listed it over here, this is also a kind of a new and emerging application in the domain of tool manipulation. Can't remember exact word for the tool, but what it does is it does sheet metal forming using a robot now, and this I would say a sheet metal forming tool. Now, previously, in order to obtain complex shape like this from sheet metal, people had to build a die, a positive and negative die, and these dies had to be machined. And these dies cost a lot. And then these dies had to be sent into a press, and the press had to be operated. So if I want to, let's say, if I want to obtain a sheet metal component like this, uh, with these kinds of complex shape embossed into it, I would need to have a purchase. So I would need to have access to a press. I would need to kind of commission a die. Then lots of money on board, and then put it into the press and obtain the sheet metal, and that's really extremely financially unviable. The financial viable option, the people are uh, so they are attaching this forming tool to a robot and moving the robot around. And the research question no, we know we have knowledge of the shape that needs to be embossed, but there's really no direct known relationship between the embossed shape and the path that robot needs to follow. But so that's the research question: what path the robot should follow in order to emboss a particular shape. But that's what people are researching on. But it's an emerging topic. That's and an example for tool manipulation. Right. A third category of category of tasks that the manipulators are engaged in is inspection either by cameras, contact probes, or measuring devices. Now, this is an example for inspection by a camera. There's nothing that I need to explain over here. There's a camera attached to the end of the robot. It moves the camera along a certain path and sends the images over processing network. And it's quite straightforward, but this is an example for kind of a combination of contact probes and measuring devices. Now, I hope you can see some laser. I hope you can see a laser line between the end of the robot arm and its station over here. Now, what the robot is doing is it's kind of measuring the profile of a turbine blade of some kind of gas or whatever turbine. Now these turbine blades have to be kept in so the shape of these turbine blades have to be kept within certain tolerances. And what the robot is doing is it's moving the probe along some specified paths. And this laser is tracking the position of the probe. It's a kind of complex application, but essentially an inspection application done by a industrial manufacturer. Okay. Uh, Now, the extent to which we study this manipulation won't be limited to taking a look at these photos, right? Using the Robotics software, we will be uh, doing some at least programming robots to inspection using cameras and measuring devices, at least in a virtual environment. We'll be developing robot cells. We'll be bringing in geometries like this, and we'll be programming robot paths that it has to follow in order to do the relevant camera. So in order to move the camera in the required path. Last year, I only did the practicals, and one of the practicals was based on simply moving a programming the robot to do a simple spray painting application. Now this year, since I have full control of the model, I'll be moving on to more complex activities like the ones that I have shown over here, right? But still in a virtual environment, since we don't have access to physical robots, at least. Yeah. And the second category of industrial robots is mobile robots, which can either use transport boxes and objects around. I would call it bulk transportation. And then we have mobile robots which carries a manipulator around. Now that might be because the factory or the workplace that the robot works in has multiple stations. But if the factory has found it financially unviable to have a robot manipulated at each of these stations, perhaps due to the fact that these stations might not be working all at once, then it might be financially viable to move around a single manipulator towards all of these stations and have it operate whenever it's needed. And the human can be moved out of the loop by using a mobile robot. And the mobile robot will carry around the manipulator from station to station whenever it's needed. Now, last year, we also had a final year project supervised by me and Dr. Akila, which attempted concept like this. So as I told you, we had a wall painting, but I don't think I've shown it to you yet. We had a wall painting robot and a wall art robot. So we also another student also tried to build at least a robot which was capable of driving between stations and positioning itself accurately through the use of fiducial markers called Aruko markers. Right? But we didn't have a physical mobile robot like this. It was just limited to a prototype. Okay, so we'll take a kind of a moderately deep dive into what articulated manipulators are. So these are also subcategories of manipulators based on the kinematic configuration. Told you before, can classify robots based on kinematic configuration. I haven't really explained what this is yet, but right now just think of it as some buzzword. Now, serial robots can further be broken down into multiple sub-configurations, and these are what I'm going to go through now. The first such sub-configuration is articulated manipulators. Now, these type of robots are what typically comes into your mind when you hear the word robot arm. That is because all of joints in these kinds of robots are revolute. By revolute, I mean the kind of joint that you see in our own arms. Right? That's the reason why these kind of things also pop into our heads immediately when we hear the term robot arm. Right? That's the reason. All joints are revolute. And yes, and based on how many joints a robot arm has, can also be broken down into 6, 7, 5, or 4 degrees. As we will learn later on in lecture 203, 6 degrees of freedom are required in order to position a particular object in space. 3 degrees of freedom to specify the location, and 3 more degrees of freedom to specify the orientation. Now that's why 6 degree of freedom robots arms are quite more ubiquitous than any of these other types of arms. And 7 degree of freedom arms, such as the one I see on seen over here, the yellow arm seen over here, kind of extend the capabilities of a 6 degree of freedom one by having, if it has to work around certain, it has to kind of crawl around or curve around certain obstacles, right? I find it quite hard to explain what it does over here using a simple photo, but when we come to the do the practicals, do the programming, I'll show you the advantages of having 7 degree of freedom one over 6 degree of freedom one. But I would say, if you imagine that your arm had another joint, think of the additional capabilities that your arm would have. And that's the reason why people have developed the 7 degree of freedom ones. But due to the limited requirement for such applications, we don't see much of these 7 degree of freedom arm models. And then we have certain applications like simply picking up a car and moving it around without varying its orientation that much. Then we might be able to make do with 5 or 4 degree of freedom robots. Right. Now, I have given a list of vendors for articulated arm manipulators. I have excluded the kind of the relatively unknown ones and non-industrial ones. So what you can find over here are very the more prominent and prominent vendors which have users in industrial applications as well. ABB and Universal Robotics and Yaskawa and Staubli. 4 of these brands have, so there are robots from these 4 brands operating in Sri Lanka. ABB, Universal Robotics, Yaskawa, and Staubli. I haven't heard of these other brands, but these are prominent brands in Celeste. Fanuc is trying to get their robots implemented in SL. I think there's one factory which has Fanuc robots as so from these 5 brands, what's operating in SL. And this Universal Robot brand and the robots developed by Universal Robotics kind of stand out from the remaining ones because they have a feature called rapid drivability, and due to that feature, we call them cobots or collaborative robots. So essentially, having that particular feature of rapid drivability makes it safe to be used alongside humans. These other non-rapid it works alongside a human and makes a mistake, it would come crashing into the human and injuries will definitely exist. But when it comes to robots or collaborative robots, with that driver will not crash, but it rather decelerate itself upon contact. Right. So we have multiple vendors for robots, and when selecting a robot, apart from the price, what else do we need to focus on? What other factors that we need to focus on when selecting a robot? Now, as we discussed, first we should figure out using the theory that I would teach in lectures 2 and 3, how many axes that we would need for the particular application, right? To see whether a 6 is enough or whether a 5 or 4 is enough. Because if we can achieve the application with the robot with a lesser amount of access, then of course it's going to be less expensive and cheaper. And then we need to figure out what the payload is. By static payload is means the maximum weight it needs to lift, and the dynamic payload is the maximum weight combined with the maximum acceleration. The reach is how far the robot will be able to reach, or how bigger the working envelope of the robot that robot is. And then we come to the factor called repeatability. And I hope you remember what repeatability is from your sensors and actuators module. And if not, then let's watch another video and see a demonstration of robot repeatability. Right now, this says that this particular robot arm has a repeatability less than 0.025 millimeters. So what that really means is, let's say you at the start of the operation, uh, in the manner that this thing does, it brings the robot to a particular location, and let us call it A. In each, this is the reading that it will give when it has. So the first mark is the reading that it would give when the robot has been brought into position A. Now, if we move the robot around, due to imperfections in the actuators, the sensors, and the gearboxes and all that, the next time around, even though we command the robot to come back to position A, the reading on the micrometer would not be this initial line. Instead, it would have some other line, right? That's due to imperfections in the components of the robot. Now, the smaller that deviation is, the lower the magnitude of repeatability and the better the robot is. Now, this in this particular robot, after doing 2 iterations of some kind of motion, we see that there's a deviation of 2.5 scales, or rather 25 micrometers. Yes, 25 micrometers, and therefore it's measured. The repeatability of this robot is measured as 0.025. I hope that's clear, but if not, simply Google repeatability tests for robots and you'll see. Now, the issue with good robots is that they have kind of minimized the information imperfections through better engineering, and have developed robots with an extremely low amount of repeatability, which cannot be detected using the micrometers that we see over here. Not for this one, but there are a few models which have such repeatability. And let me show you one such. So this also is a robot, called a parallel hexabot robot. And the robot models developed by the company Physics Instrument has a repeatability less than 1 micrometer, and using this kind of gauge that cannot be detected. Right? And when people say that it has this amount of repeatability, it really means this particular robot has a repeatability in the nanometer range. Right? It's not zero, but it's in the nanometer range. It has been, the magnitude of repeatability has been lower. So that's what repeatability is. Essentially, you program, if you hold a robot at an initial position of A and let it move around for a while and command it to come back to A, it won't be exactly at the initial position. There would be a small deviation measurable in the micrometer range. Right? So based on your application, you have to select the repeatability. Now, when I was working at Orange, the repeatability requirements were in hundreds of micrometers or 1 decimal point of a millimeter. That was enough. Right? But when it, for certain applications that I'm working on now, the repeatability needs to be in the sub-micrometer range. So that depends on the application. Typically, the bigger the object that you're handling is, uh, the, the higher the magnitude of repeatability it needs to be. So if you are handling a car like this, then the repeatability would be okay with having a repeatability of 1 millimeter or so. Same could be said for a spray painting or a welding application. But if you are working with picking and placing electronic components, then definitely the repeatability needs to be in the micrometer range. And as for back drivability, I've already described it. It's the feature that kind of decelerates the robot on collision and so on. And these are industrial robots that we are talking about. So they need to be resistant to water or dust. Particularly if a robot is doing powder coating, it definitely needs to be dust resistant. Otherwise, within a matter of days, the dust from the powder from the powder coating spray would clog up the actuators, and the robot would bind itself. And similarly, there are robots which work in environments which have water around, and in that case, it needs to be resistant to water. So you need to check the documentation of the manipulator models and see whether it has these criteria. It meets whatever criteria that you're looking for. And in cases like food preparation applications, it must ensure that any oil or any fumes from the robot should not drip onto the food. Right? That those kinds of requirements can be categorized as contaminant-free operation. And nowadays, simply having a robot which can be programmed using the vendor's programmer is not really preferred in selecting a robot manual. So previously, all the robots, I would say back in 2010s also, all these robot models came with a vendor provided programmer and a teach pattern. Now, even still those are provided, but nowadays these also provide fun. These also support programming using third-party programs. Now, Robotics is a such third-party program offline programming software. And, there are certain few others as well. Now, if the robot model supports that kind of third-party programmers, then what you need to purchase as a purchase for the purpose of programming is one such software like Robotics. Then whatever model, so if you need a robot from another brand, then you don't need to learn the whole programming software of that other vendor. you can simply stick with Robotic and program whatever robot from whatever brand that you want. And yeah, in today's day and age where digital twins are becoming a thing, the robot should also provide support for condition monitoring as well. Or industrial IoT support should also be available in the manipulators. Even if your factory does not have such features at the moment, at least in a few years it will have. And then if your robot that you have implemented does not have those supports for IoT, then you'd have to build them by yourself or go with a robot that has. But, so those are the kind of uh, primary of the surface selection factors. These aren't really, I haven't really gone that deep into selection factors, but these are what you need to look at least off the surface. And these selection factors would stay the same for rest of the models that I'm showing. So one such model is the Cartesians and the cylindrical manipulators. I'm not going to go through the whole slide, but you can see that compared to the envelope of the articulated robot, the envelope of the Cartesian is much less, and the cylindrical has some kind of an envelope in between. But the thing is that these Cartesian robots kind of have screws built into them, at least for the axis dealing with working against gravity. And in that case, uh, unlike revolute joints, these screws or prismatic joints they perform well against gravity. But adversely, they are also slower due to the reduction in the screws. So Cartesian robots and cylindrical robots are kind of the slowest among all manipulator types. Let's just take a look at a 6 degree of freedom Cartesian robot. It has 3 axes, prismatic axis, so those kind of things you must be familiar with. And at the end, they have a 3 degree of freedom revolute joint. This is kind of a robot which combines both worlds of a standard Cartesian and that of a articulated arm. But still, you can see that the working envelope is much less. However, due to the 6 degree of freedom, 3 plus 3 plus 6, due to 6 degrees of freedom, it can manipulate the tools that it's using in all 6 required axes. And this will be a final year project that I'll be working on this year, that will be made available to you this year, also supervised by me and another lecturer. So I plan to break this down into 2 components: the 3 degree of freedom Cartesian robot and the 3 degree freedom wrist, and later on combine those 2 in order to provide that 6 degree of freedom hybrid Cartesian robot. And then we have the selectively compliant assembly robot arm, or SCARA, uh, which, as I mentioned earlier on, was developed by initially developed developed by university in Japan. Now, so these were developed way back, and these are extremely fast because uh, there's only one joint that works against gravity, and all the remaining joints do not. So the joint that works against gravity is not that fast, but the remaining joints, since they do not have to have high gear reductions to compensate for gravity, then they can focus on being fast. And therefore, it has resulted in Scaras being one of the fastest robots, at least a bit slower than the Deltas that you see. But when it comes to fast assembly operations, this is the go-to type of robot. but it also loses a few degrees of freedom. It's not a 6 degree of freedom robot. So therefore, it cannot manipulate uh, objects into all the required positions. I also have a video on this just to show you how fast SCAR robots are. But this is from the German brand Saubli, and it's not a fast forwarded video. Right? Uh, as I said, it's not fast forward. This is how fast SCARAs can be. That's big. Yeah, and further to my point, if you look closely, you will see that while the two revolute joints, the motions of the two revolute joints aren't that visible. You see that compared to those two, the prismatic joint going up and down is visible. So the joint working against gravity is not fast, but the remainder is fast. And this is also kind of an easy robot type to build. Last year, two of your seniors built two SCARA robot arms, three of them, I think. Uh, so one was developed for as a part of a automated screw driving cell that I planned. So this was built using wood as the structural elements and using motors scavenged from a junkyard or something. I think this particular SCARA robot arm was developed for less than 10,000 rupees for a screw driving automation as an automation cell. Mm, and it uses, I think it used GRBL or yeah, I think it used, I'm not exactly sure, but I think they used rubble to handle the inverse kinematics and robot motion. So they would feed in the G code as to where it should need to travel, and the G code interpreter, which is not developed by them but developed by someone else, handles the rest. And then we have a vertical SCARA, but unlike the regular SCARA, I wouldn't say that all these joints work against gravity, but he had used counterbalancing counterweights in order to compensate for gravity so that he could use lesser powered motors to drive some lengthy links against gravity. So now this was the robot developed for wall painting applications, and by one of both developed by your immediate team. And finally, we have parallel manipulators. These are kind of the deltas are the fastest manipulators existing right now. And it happens so due to the fact that once again they also have only revolute joints, but uh, all these links work in a manner similar to what we see in a lever. And due to that fact, there's a lever advantage obtained, and that is and that is used to obtain gains in speed. But the thing is, just like you see in the photo over here, the envelope is, and compared to what's being picked up. So this whole gigantic robot is used to pick up this small package, I think. Compared to what's being manipulated, the robot is extremely large. So that's not your concern, then that's okay. But that's kind of the only issue with regards to the delta manipulation. Now, in addition to these delta that I have shown here, there are a few esoteric models or few relatively unused parallel manipulator models called the Stewart platform, the Tricept, or the Tripteron. I have given links to YouTube videos over here, so you can go over there and check them out yourself. And that brings the end of our lecture. Now, in multiple slides, I have given links to YouTube videos, so check them out you can click on those hyperlinks and go to the relevant YouTube videos or check them out. But, so that's it for today's lecture. Participants have left. Any questions? No questions. Okay. I'll end the lecture for today. Then you can. I'll create the module on the LMS as well, and also send the recording once Prashant sir sends it to me. Perhaps tomorrow or day after tomorrow, the link to the recording will be uploaded to the LMS. Just make sure that you download this video, because these aren't available after 30 days from record, right? Okay, so that's it. So why don't you leave the meeting so I can figure out who's sleeping and who's. I would like you to leave the meeting. So if you don't leave the meeting now, I'll consider that you are simply switching on the Zoom and sleeping, right? So one guy is not sleeping, right? Okay, but okay. Thank you very much. Then, okay, 525 and 561. Are you sleeping? Oh, right. I guess they are. So, okay.